grammar rules. So there are two ways to which we can remove the non-determinism from the grammar. The first one is a left factoring of the grammar, and the second one is through removing the left recursion from the grammar. So what we'll do today, we'll learn the first technique, how to do left factoring of the grammar. So what is a left factoring in the grammar? Let us understand first. A known terminal with two or more productions whose right-hand sides start with the same grammar symbols adds non-determinism to the parser. So as you can see here, a known terminal A produces alpha beta 1, alpha beta 2, alpha beta n, and gamma. So this is a general form of the context-free grammar. The left-hand side is a non-terminal, while the right-hand side is a combination of terminal and non-terminal. So as you can see here, A gives alpha beta 1 or alpha beta 2 or alpha beta n or gamma. So you can see the alpha is common in this grammar rules, while gamma is a grammar rule in which there is no common part like alpha. So the problem of non-determinism arises because all these production rules starts with a non-terminal alpha. So now what will happen? That because alpha is common, we cannot tell that which rule will finally give us the derivation of the string. Should we use alpha beta 1, or should we go for alpha beta 2, or we should try alpha beta n, because all starts with alpha. All these n rules starts with alpha. So it leads a non-determinism, right? So to achieve a determinism, what we'll do, we'll write a new production rule. We'll take the alpha common. We'll write A gives alpha. We'll get A gives alpha. Then we have a new non-terminal AR. It is a new non-terminal, and we have gamma. And we have gamma. So now for this AR, for this new non-terminal AR, we will write the remaining portion of this production rules. So we'll write beta 1 or beta 2 up to beta n. You can see here that we are not touching the rule A gives gamma. We are not touching the rules A gives gamma because there is no common substring in that production rule. So it is with a non-terminal A. So this will not change the meaning of the grammar. A gives gamma as it is, and we'll take a common element alpha from rules up to beta n. So we'll write A gives alpha AR, and we'll replace AR with beta 1 or beta 2 or beta n. So you can see actually now beta 1 is a string which is starting with a different symbol. Beta 2 is a string which starts with some another symbol, and beta is a string which starts with some another symbol. So now it gives a determinism to the derivation process because alpha is common. So up to alpha, the derivation steps are same because we are always going for leftmost derivation. We are always going for leftmost derivation. So up to alpha, everything will be common. So the steps will not affect it. And once you derive the substring alpha, then it is very easy to identify which is the right production rule for the remaining derivation. Should we go for AR gives beta 1, or we should go for AR gives beta 2, or we should go for AR gives beta n. So you will not find any difficulty in this. So now let us apply these rules. Let us consider this grammar. We have E gives T plus E, or T minus E, or T. Right? We have written the rules at the top. Right? So you can use that rule again here. So E gives T plus E or T minus E or T. You can see that T is common. The T is common in all the three rules. So if I match this, then we can say T is equal to our alpha plus E is equal to beta 1 minus E is equal to beta 2, and we can say null is our beta n. And here there is no rule like gamma. There is no rule like A gives gamma. We have T plus E or T minus E or T. So out of this, we'll take T common. So we will write E gives T E R. We'll take a new non-terminal ER, and for the ER, we'll write the remaining portion, that is plus E or minus E or null, because in the third rule, null is left. In the third rule, null is left. So we'll write E gives plus E or minus E or null. Similarly, in the second rule, you can see T gives F into T or F. T gives F into T or F. So again, F is common. We'll take the F common because it is like alpha, and beta 1 here is star T, and beta 2 here is your null. We have only two rules. So beta 1 and beta 2 are there. Beta 1 is star T and beta 2 is your null. So we'll write T gives F, and then for remaining portion, we'll introduce a new non-terminal TR, and for TR, we'll write star T or null, star T or null. You can see that when you apply a leftmost derivation, right, from the starting symbol E, you will get the first step as E gives TER. So T is the leftmost non-terminal. So you will process it further. So you will get FTR. Again, we have only one rule. So it is a deterministic step. Now after F, we'll get A, TR, ER. What we'll get? A, TR, ER. So A is a terminal. So now we have to focus on TR. Now when we focus on TR, again you can see, we can clearly identify which rule is applicable. If we require a multiplication symbol, we'll select the rule TR gives star T. We'll select TR gives star T. If we do not require a multiplication symbol, we'll select null. Similarly, in ER, if we need plus symbol, we'll select plus E as a rule. If we require a minus subtraction operation, we'll select rule minus E. And if we don't require any of these symbols, we'll select null. So basically, it is a determinism. We know which rule is applicable at a particular point. So let us see here. We have this example. We want to derive A. We want to derive only A. So as you want to derive only A, right? Now we have, if you use the original grammar, from E, we have two options, T plus E or T minus E or T, as you can see, right? In this grammar, we have three options for E, original grammar, T plus E, T minus E, and T. And we don't know which is applicable. So we have to do again a trial and error. Now, in case of left factored grammar, we don't have any alternative for E. We are selecting E gives TER. We are getting E gives TER. Now for this T, we'll select FTR. We'll select FTR. So it is here. T is replaced with FTR, ER. So it is the leftmost derivation. Now we want to derive A. As we want to derive A, we'll replace F with A, because again it is a determinism. We'll get TR, ER. Now our requirement is, we have already derived A. After that, it is the end of the input. As it is the end of the input, I will replace TR with null. So we'll get AER. Now we have already reached end of the input. So we'll replace ER with also null. You can say it is a deterministic thing. You don't have to we do not face any problem when we derive the string. Now, in case of non-deterministic grammar, right? In case of our original grammar, we have to do a trial and error. T plus c will try. If it fails, we'll try for t minus c. If it fails, we'll try for e gives t. So after doing all these attempts, at the third level, we'll get t when the previous two attempts failed. Again, from t, we have two options in the original grammar: f into t or f. It is f into t or f. So we have again two options. We'll try f into t, and that path will fail. It will stop. We'll try the another path. T gives f, and that f will give us a. So you can see, as compared to original grammar, this left vectored grammar adds determinism in the derivation process. It adds determinism in the derivation process. So what is the advantage? That we can use this left vector grammar in the compilation process, which is not facing any problem of non-determinism. Let us have one more example here, right? So this grammar which you have seen, so this grammar is if expression, then statement, else statement, a dangling else grammar in a small form. Here it is written: if expression, or we can say condition, then statement, else statement. So if it is an if else statement. Second option is only if statement, if expression, condition, then statement, and last we'll replace statement with any simple statement. And for condition, we'll replace expression condition with B. So again, you can see here that if you match this with our general template of left vector grammar, then our alpha is IETS. IETS is the alpha. It is common between the first two rules. It is common between the first two rules. Then, as you can see, that the beta 1 is ES. This beta 1 is ES. Then we have beta 2, it is null, and gamma, here gamma is there. Gamma is A. So S gives A, we'll write as it is, no change. S gives A as it is. We'll take the alpha common. So IETS alpha, that is IETS alpha, will introduce a new non-terminal. That new non-terminal is SR here. Now for SR, we'll write beta 1, so it is ES, or beta 2, which is null, and E gives B. E gives B. So here you can see that because both these first rules and second rule, first and second rule of S, both starts with I. Both starts with I. So it is difficult to identify which rule we should apply. Both starts with I, so it is difficult to identify which rule we should apply. So it gives us a non-determinism if we consider the original grammar. So let us see that can we use a left vectored grammar to solve the problem. Now here you can see from S we are having IETS, ES, or IETS. Again we have to go for trial and error because we want to derive this string IBT, IBT, AEA. Right? We want to derive this string IBT, IBT, AEA. So now if you use the original grammar, IETS, ES, or IETS. So again, we have to do trial and error, and any one of the path will succeed. So now let us see how we can use a left vectored grammar to achieve the goal. So now from S, we have IETS and SR because we have only one option. So we have achieved I. Now the leftmost non-terminal is E. Now the leftmost non-terminal is E. We'll replace E with B. we'll get I, B, T, S, and SR. I, B, T, S, and SR. So now if you compare with the required string, we have achieved T and T. So now next we want I. So again, we'll select the non-terminal S. We'll replace with IETS SR. So that is what we are doing here. I am replacing S with IETS SR. I am replacing with IETS SR here. So again, I have achieved I. Now I will replace E with B. So we have achieved this IBT, IBT. All these are terminals. IBT, IBT. Then we have S and 2 times SR. S and 2 times SR. So we have achieved IBT, IBT. Now we require A. Now we require A. So I will replace S with A. Again, it is a deterministic step. We are getting IBT, IBT, A. And we have 2 times SR. We have 2 times SR. Now after A, we require E. We require E. So now, if you look at this rule for SR, I can replace SR with ES because my requirement is E. Because my requirement is E. So I am replacing that. So IBT, IBT, A, ES, SR. It is ES, SR. We have achieved E. Now I will replace S with A. We are getting IBT, IBT, AEA, AEA, and SR, where SR is replaced with null because we have reached the end of the string. So we are getting IBT, IBT, AEA. Now, because as I told that through left factoring or left recursion, we cannot convert every ambiguous grammar into unambiguous form. We cannot convert every ambiguous grammar into unambiguous form. So here you can see that there is also a second alternative. If I replace SR, the third step from the last, I am talking about third step from the last. So if I replace SR with null, if I replace SR with null, then you can see we have a second alternative, IBT, IBT, A and SR, A and SR. Now from this SR, I can replace with ES, I can replace with ES because we have 2 SR here. We have 2 SR here in the derivation. So either I can replace first SR with null or I can replace second SR with null. So we have 2 different options here. So IBT, IBT, AEA, AES, AES. And then last S we are replacing with A. The last S we are replacing with A. So as you can see here, because our grammar is an ambiguous grammar, as our grammar is an ambiguous grammar, we cannot achieve the complete goal through a left factoring. For some grammars, it will work. For other grammars, it will not work. We have this very important observation here that for some ambiguous grammar, we can apply a left factoring and we can get a completely deterministic path. While here you can see, we have 2 derivation trees again for SR. Either I can replace first SR with null or I can replace second SR with null. And we have 2 different derivation trees. So that means if the grammar is ambiguous, through a left factoring, we can achieve some level of determinism, but it is not necessary that we'll get a completely deterministic path. We'll get a completely deterministic path. So we cannot remove ambiguity from the grammar always. We have one more example here. You can see S gives $T. So I hope there is no query in the first and second example. If you have any query, you can write in the chat window. Yes? Do you have any query? If you have any query, please mention in the chat window. Yes, can we proceed further? Yes, can we proceed further? I hope you are able to hear me clearly. Yes, can we proceed further? Okay, so let us continue. I will assume that this is the response of all, or at least majority of the students. I know it is an afternoon time, and it is a, I think, post lunch session for all of you. So I expect that I don't get so many responses. Many of you are taking a nap right now. Yes, are you taking a nap? So can't you hear you? So please mention where the query is. If you mention, then I will tell you where is the query. There is one more example. We have S gives T dollar. So and T gives, we have within bracket T or opening bracket, closing bracket T, third alternative, opening bracket T, closing bracket T, and fourth one is opening and closing bracket. So if you look at these four different rules, there is no common parameter. S gives TS. We have only one rule with S, but in the second rule T, we have four alternatives and opening bracket is common. Opening bracket is common. So that opening bracket will act as alpha. Beta 1 is T closing bracket. Then closing bracket T beta 2. From the third alternative, T closing bracket T is the beta 3. And fourth one is a closing bracket. So right now we are discussing this line. We have the opening bracket as a common parameter. We have opening bracket as a common parameter. So it is alpha. Beta 1 is T closing bracket. Beta 2 is closing bracket T. Beta 3 is T closing bracket T. And beta 4 is the closing bracket. So now we'll rewrite this rule. So S gives T dollar, right? S gives T dollar. There is no need to apply left factoring on this line. Now we'll take the T gives opening bracket TR because opening bracket is common. And for TR, we have the remaining portion. So beta 1, T closing bracket or beta 2, closing bracket T or beta 3, T closing bracket T or beta 4, that is closing bracket. So this is how we are getting this left factoring of the grammar. So I hope you are getting this, how we have done this left factoring. Okay, so now let us apply this. As you can see here, still we have this common alternative, because whenever there is a common alternative, we need to apply a left factoring, because if it is a common alternative, it will lead to a non-determinism. It will lead to a non-determinism. So as you can see here, right, we have two common alternatives, T closing bracket and T closing bracket T. These are the two common alternatives. And the another common alternative is closing bracket T in the second rule and closing bracket in the fourth rule. So again, we have to apply a left factoring. Again, we have to apply the left factoring. So you can see here that S gives T dollar as it is. Now T gives closing bracket TR, it is as it is. And now here we are applying a left factoring. As you can see here, we are writing TR, we are introducing a new non-terminal. So we are writing T closing bracket from the first and fourth. T closing bracket is common, and we are taking a new non-terminal M. Similarly, from the second and fourth rule, we are taking the common alternative, that is closing bracket, and will introduce a new non-terminal N. Will introduce a new non-terminal N. Now for non-terminal N, we are writing the remaining portion from the first and third rule. So from the first rule, the remaining portion is null. From the third rule, the remaining portion is T. So we are writing T or null. Similarly, from the second and fourth rule, we'll write down the remaining portions. So N gives T, that is the common portion from the second rule, and null is the common portion, remaining portion from the last rule. So T is the remaining portion from the second rule, and null is the remaining portion from the last rule. So we are getting this TRMN. Now, as you can see, that M and N, right? M and N both are same. As you can see here, M and N both are same. So we'll write only one variable for that. So we can rewrite as TR gives T closing bracket M or closing bracket M. So we'll replace N with M, and we'll remove the non-terminal N. We'll remove the non-terminal N. Is this clear? Yes. Is it clear now? We have done 3 examples. Okay, in the third line, what we are doing, we require a common, we want to do a left factoring. So first and third rule, we need to apply a left factoring on it. And similarly, second and fourth, because closing bracket is common, we have to apply left factoring on it. So we have to apply 2 left factoring on this TR. We have to apply 2 different left factoring on TR. So if I apply a left factoring on the first and third rule, because we have common portion is T closing bracket. So we are writing TR gives T closing bracket M from the first and third rule. T closing bracket is the alpha part. So we are writing T closing bracket M. We are introducing a new non-terminal. We can give any name. Similarly, from the second and fourth rule, closing bracket is common. So it is our alpha. So we'll write closing bracket and we'll introduce a new non-terminal, that is N. That is N. And in M and N, we'll rewrite the remaining portion. we'll rewrite the remaining portion. So M is generated from first and third rule. So we'll write the remaining portion from first and third rule in M, while in the second and fourth rule, the remaining portion will write with N. Yes, is it clear? Because this is the base for compiler construction. You have so many examples of this left factoring of grammar. You have to apply that several times in compiler construction. So if you have any doubt, you can ask. Is this clear? Okay, so at least these four people are not taking the nap. Priyank, Lao, Munaf, Abhi. So I hope it is clear now. Left factoring. You can do a left factoring on any grammar. Yes? Yes, can you do a left factoring? Okay, so let us go to another topic. I'm sharing another slide with you now. So why we are doing left factoring? Keep that reason in your mind that we want to achieve a determinism. We want a deterministic grammar, so that if there is a determinism, then you have always one leftmost unique derivation. We want a unique leftmost derivation always. We cannot have more than one derivation tree. Also, we want to achieve determinism and we want to avoid backtracking. So if we have one unique path, one unique leftmost derivation, it will be very easy to validate the thing. We cannot have multiple derivation possible, right? That's why we are doing a left factoring on the grammar. Okay, so I am sharing another slide with you now. Okay, so those who have missed the train, this is another option to understand the thing. That so far we have generated a non-deterministic PDA by using analysis, right? We have defined the rules Q0, Q1, push, pop, ignore operations. But there is another way to generate a non-deterministic push-down automata based on the algorithm. But the rules generated here are different from the previous one, right? But there is one algorithm through which we can also generate a determinist rules for the non-deterministic push-down automata. So it is telling that if you want to get a non-deterministic top-down PDA for any grammar, then we can do it with always three states: Q0, Q1, Q2. Always we have three states in the non-deterministic push-down automata table. Our accepting state will be always a Q2 state. Always we have a Q2 state. Our stack alphabet will be set of non-terminals of the grammar, union set of terminal symbols of the grammar, union a Z0, union Z0. So this is what will be the case. Clear? When you consider this, right, our set of non-terminals of the grammar will be the stack alphabet, union input symbols, terminal symbols of the grammar will be the stack alphabet, and Z0 will be the stack alphabet. So it is telling that first rule will be always Q0 null Z0, right? This is the way to write down the rules for non-deterministic PDA. We can directly get a non-deterministic PDA table using this. So Q0 null Z0, which is highlighted with yellow color, the first line. So Q0 null Z0, and we'll go to a Q1 state and we'll push starting symbol of the grammar on the stack. So we are getting Q1 as Z0. will consume null from the input. So Q0 null Z0, Q0 null Z0, and we'll go to a state Q1 SZ0. So we are getting S on the stack because we want to generate a non-deterministic PDA and we want to achieve a parsing, top-down parsing, right? We want to derive the string from the starting symbol. That is the ultimate goal. So Q0 null Z0 will give us Q1 SZ0. That is the first rule. Now similar to that, we have only one move for the acceptance, Q1 null Z0. So Q1 null Z0 will give us Q2 Z0. It is Q2 Z0. Second rule, which is highlighted with yellow color. What is S? Obviously, it is a starting symbol of the grammar. V sigma S and P. It is V sigma S and P. V is the set of non-terminals. Sigma is the terminal symbols of the grammar. S is the starting symbol of the grammar. And P is the set of rules. So now let us apply these two steps. Let us apply these two steps. Then we'll understand the important rules. So now here you can see we have the grammar. S gives within bracket S or SS or null. S gives within bracket S or SS or null. So as per the rule 1, it is Q0 null Z0. We'll write Q1 as Z0. So it is a fixed step. It is a fixed step. Always we have to write this. S will be the starting symbol of the grammar. Right? Whatever the starting symbol we are using, we have to write that. Q0 null Z0. Q1 SZ0. It is Q1 SZ0. We are pushing the starting symbol of the grammar on the stack. Our state will be a Q1 state. Similarly, you can see the last rule. That is for acceptance. Rule number 5. Q1 null Z0. Q1 null Z0. Rule number 5. It is Q2 Z0. So first and fifth rule, right? That is fix. First is to push the starting symbol, initial move on the stack, and the last rule, that is for the acceptance. Now the remaining rules depends on the grammar. The remaining rules depends on the grammar. So these rules are recursive rules. You can see that for every A belongs to V, which is highlighted with blue color. For every A belongs to V, this is highlighted with blue color. So for every non-terminal of the grammar, we'll write down the rule as we'll write down the rule as Q1 null A. We'll write down the rule as Q1 null A, where A is the non-terminal of the grammar. We have a rule Q1 null A, and on the stack, the move will be Q1 alpha. What is alpha? Alpha, A to alpha is a production rule. A to alpha is a production rule in the grammar. So it is a push operation, we can say. It is nothing but the push operation. For every non-terminal of the grammar, A belongs to V, Q1 null A, where A is the non-terminal of the grammar, Q1 alpha, where alpha is the right-hand side of the rule. So this we have to write for every non-terminal. It is a recursive rule. We have to apply several times. So here you can see that rule number 2. Let us see, it is rule number 2. Right? We have how many non-terminals here? We have only one non-terminal S. We have only one non-terminal S. So rule number 2 is Q1 null S. Right? Q1 null S. And what is the move? It is Q1 alpha. What is alpha? Alpha is the right hand side of the production. Alpha is the right hand side of the production. So we'll write Q1. Now we have three alternatives. We have three rules. We have three different alternatives. So it is within bracket S. Then we have within bracket SS. Within bracket SS and null. So we'll write Q1 within bracket S, then Q1 SS and Q1 null. It is Q1 within bracket S, Q1 SS, and Q1 null. We have three alternatives. We are writing all the three here. So it is applicable to all the non-terminals of the grammar. It is applicable to all the non-terminals of the grammar. Now, the last one is for every terminals of the grammar. For every sigma belongs to capital sigma. For every small sigma belongs to capital sigma. Right? That is a terminal symbols. It is a pop rule. Q1 small sigma. It is highlighted with green color. Q1 small sigma comma small sigma. So it is your state, input, and top of the stack. So Q1 small sigma and small sigma, which will give us Q1 null. So we'll match input symbol and the top of the stack symbol. This rule tells that we'll match the input symbol with the top of the stack symbol, and if they are matching, we'll pop the thing Q1 null, Q1 null. So it is for every terminal symbols of the grammar. So as you can see here we have terminal symbol opening bracket. Another terminal symbol is the closing bracket. So we have to apply this rule two times. We have to apply this rule two times. So it is Q1 opening bracket, because what is the rule? Q1 small sigma. So here you can see we are matching opening bracket with the opening bracket. We are matching opening bracket with the opening bracket, and it is Q1 null. It is Q1 null. Similarly, another terminal symbol is the closing bracket. Another terminal symbol is the closing bracket. So we'll write Q1 closing bracket and closing bracket. So we'll match input closing bracket with the top of the stack closing bracket, and we'll write Q1 null. So basically in this NPDA construction, we'll generate the string on the stack. When we generate the strings on the stack, and when the input character is matching with the top of the stack, that will be eliminated. That will be eliminated. So basically here you can see from this set of rules, the first is initialization. We'll push starting symbol of the grammar on the stack. The second rule for acceptance, the last one, Q1 null Z0 will get Q2 Z0. Then we have two recursive rules, Q1 null alpha, Q1 null A, which will give us Q1 alpha, which will give us Q1 alpha. Similarly, for terminal symbols, we have Q1 small sigma, which will give us Q1 null. So that is applicable to every terminal symbols. So now using these rules, now let us see how we can generate the string and how we can reach to acceptance. So now here you can see we'll start with Q0, and we have some string. The first step, Q0, we have some string opening bracket, nested open. We have two consecutive opening and closing brackets, and it is nested. And then last is Z0. So now, as per the rule one, which we have written, we'll push S on the stack. So Q0 null Z0 will consume null, and we'll push stack symbol, starting symbol S on the stack, Q1 SZ0, Q1 SZ0. So that is what you can see. Q1, we are consuming null from the input, which is highlighted with the blue color, and SZ0, it is SZ0. Now, because S is the non-terminal, we'll apply only rule number 2. Q1 null S, again we'll consume null. Again we'll consume null. Now it is a non-deterministic PDA because we have three different alternatives. It is a non-deterministic PDA, but here to save the space, I am showing directly the rule which is the correct rule. Otherwise, you have three different branches here. At this level, you have three different branches. Clear? But I am showing only the correct path. So Q1, then we are writing, we are replacing S with opening bracket S. We are replacing with opening bracket S. The reason is we require opening bracket. We need an opening bracket. So we'll select that rule, opening bracket S, closing bracket. right? Which is the correct path. Now what will happen? That opening bracket in the input is matching with the opening bracket on the stack. Opening bracket in the input is matching with the opening bracket on the stack. The reason is that when you are getting a terminal symbol on the stack, it will match with the terminal symbol in the input. At that time, we'll perform the pop operation. We'll perform the pop operation when the terminal symbol on the stack will match with the terminal symbol in the input. So we have pop operation, that is the step number 3, Q1, opening bracket, closing bracket, again opening bracket, closing bracket in the input. Then on the stack it is capital S, closing bracket, Z0. So again we are getting non-terminal S on the stack. So now again we have to apply rule number 2. Again we have to apply rule number 2. We have 3 alternatives, but really I am showing here only the correct one because we require a pair of 2. So we are using Q1 SS. So I'm writing that we are consuming null always from the input. So Q1 we have SS, closing bracket, Z0, the fourth line. It is the fourth line of the step. It is the fourth line of the step. SS, closing bracket, Z0. Now again we have S, which is a non-terminal. So we have to consume null from the input, and I will replace S with Q1 within bracket S. I will replace with Q1 within bracket S. Now, as we are getting the terminal symbol on the stack, it will match with the terminal symbol in the input, and we'll apply the pop rule. We'll apply the pop rule. Q1 opening bracket in the input, opening bracket on the stack, Q1 null. Rule number 3. So we are getting this step number 5. And from that we are getting step number 6. It is the step number 6. Now we require closing bracket in the input. We require closing bracket in the input. So we'll replace S with null. So we'll apply the rule number 2 again, non-terminal S, Q1 null, Q1 null. So we'll get step number 7. We'll get step number 7. Again, the closing bracket in the input will match with the closing bracket on the stack. We'll apply the pop rule. We'll cancel it both. We'll get the step number 8. Again, in step number 8, we require opening bracket. We require opening bracket. We'll replace S with within bracket S as per the rule 2. We'll consume always null in the input. Now again we have opening bracket in the input, opening bracket on the stack. We are getting step number 9, and from step number 9 we'll get this step number 10, right? We'll remove this opening bracket from both the sides, from the input as well as from the top of the stack, using the pop rule. So now we have step number 11. We have a step number 11. We are removing S from the stack using rule 2. We have a step number 11 using the rule 2, Q1 null. Using Q1 null, we have this step number 11. Then we have pop rules applicable. So we are getting step number 12, Q1, closing bracket in the input, closing bracket on the stack, and Z0. Again, we'll apply the pop rule. We'll get Q1 null Z0. And this will give us Q2 null Z0, the acceptance step. It is the acceptance step. Q1 null Z0, it is Q2 Z0. So what you have to remember here, that we can construct any non-deterministic PDA from the grammar. If you know the correct context-free grammar, using this method, you can always get correct NPDA. The first step is fixed, Q1 SZ0. The last step, acceptance, Q2 Z0, it is fixed. And then we have two recursive rules. one for every non-terminal, and another recursive rule for every terminal symbol. For every terminal symbol. But you should know the grammar. If you don't know the correct grammar, you will face the problem. So now we have one more example here. So now you can see, right? You will see here that the starting symbol of the grammar is S. So now, as per the first rule, initialization, we are writing here Q0 null Z0, Q1 SZ0. Q0 null Z0, it is Q1 SZ0. We are pushing S on the stack. Similarly, we have to write the acceptance. So that is last one, Q1 null Z0. Q1 null Z0, it will give us Q2 Z0. It is Q2 Z0. Now for every non-terminal of the grammar, we have to write the rules. So we have three non-terminals here, S, T, and F. We have three non-terminals here, S, T, and F. So for S, we are writing Q1 null S. You can see these rules are there, Q1 null S. So we have two alternatives. So Q1 S plus T, and the second alternative is Q1T. So always we are getting a non-deterministic push down automata here. The reason is we have more than one alternative. We have more than one alternative. So we are always getting a non-deterministic push down automata. Similarly, for non-terminal T, we are writing Q1 null T, which will give us Q1 T into F and Q1 F. It is Q1 T into F and Q1 F. We have third non-terminal F, so we'll write Q1 null F, the Q1 null F, which will give us Q1 within parenthesis S and Q1A. It is Q1A. Now for every terminal symbol of the grammar, we have to write the rules, which is a pop rule. Which is a pop rule. So how many terminal symbols we have? The plus is a terminal symbol. Multiplication is also a terminal symbol. Opening parenthesis is also a terminal symbol. Closing parenthesis also a terminal symbol. So we are writing four rules here. Q1 plus n plus. We'll write Q1 null. Q1 plus plus. So it is Q1 null. So basically when plus is in the input and plus is on the top of the stack, we'll apply the pop rule. So basically you have observed that we are generating the string, we are deriving the string, a leftmost derivation on the stack. When we get the terminal symbol on the stack, we'll match with input symbol and we'll pop the both. Right? That is what we are doing. We are consuming the input symbol and we are popping the top of the stack symbol. So we are deriving a leftmost derivation on the stack basically here. When we get a terminal symbol on the top of the stack, it will consume the terminal symbol from the input and will proceed further. Now another terminal symbol is multiplication. So you can see the first rule at the top, Q1 star in the input, star on the top of the stack. We are getting Q1 null. We are getting Q1 null. Similarly, we have opening parenthesis. So Q1 opening parenthesis in input, opening parenthesis in the on the top of the stack. So we are getting Q1 null. And similarly for the closing parenthesis. So basically you can count how many rules will be there in MPDA using this method. One for initialization, one for acceptance, three for terminals, non-terminals, and four for terminal symbols. So we have total 9 rules. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Because we have 4 terminals. We have one more terminal is also there, A. So we have 5 terminals. So Q1 AA, which will give us Q1 null. 5 terminals, 3 non-terminals, 5 plus 3, 8. 1 for initialization, 9, and 1 for acceptance, 10. So you have 10 rules here: 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I hope it is clear. Let us apply it. So now using these rules, Q0, A plus A, and Z0. So we'll generate a leftmost derivation on the stack. We'll generate leftmost derivation on the stack. So we'll apply the initialization first. We'll initialize the thing for leftmost derivation. So Q0 will be converted to Q1, A plus A, and top of the stack will be SZ0. So now from S, we'll apply the rule. Now it is a non-deterministic PDA. So we have two alternatives. We have to apply both. But here I am showing the correct path. You have to ideally apply both the alternatives, left and right branch. But here I am showing the left branch, the correct branch, basically. So we are getting Q1, A plus A, S plus T, Z0. S plus T, Z0. Now for S, again we have two branches, but I am showing the correct path. So Q1, A plus A, T plus T, Z0. It is T plus T, Z0. Now T is replaced with again two branches. So I am showing the correct branch. Q1, A plus A, F plus T, Z0. F plus T, Z0. So we have Q1, A plus A, then F is replaced with A. Again here we have a non-determinism. We are applying the correct path. So A plus T, Z0. A plus T, Z0. Now as A is in the input and A is on the top of the stack, we'll apply a pop rule. Similarly, plus is in the input and plus is on the top of the stack, we'll apply the pop rule. So we are getting the last step in the first column, Q1, A and TZ0. Q1, A, TZ0. Now for T, we'll apply the rule. We have two branches, T into F and F. So we'll show the correct path. Right, so we're replacing T with F. So we have Q1A, FZ0. Now again for F, we'll select the correct path, Q1A and AZ0. Now this A and A will cancel out using the pop rule. So it is Q1 null Z0. We are getting Q2 Z0. We are getting Q2 Z0. Similarly, we can apply this kind of technique for this kind of grammars. So I hope it is clear that we have this well-known language, a raised to I, b raised to j, c raised to k, j is equal to I plus k. So what is the rule? That you should know the correct grammar. If you know the correct grammar, you can easily apply this method. So can you tell how many rules will be there for non-terminals? How many rules will be generated for non-terminals in this grammar? If you can mention in the chat window the number of rules which can be generated from the non-terminals using this grammar. Yes, if anyone can write. So I hope you are getting this. Try to generate the NPDA for this grammar because practice is required, definitely. Thank you all.